Today we're going to talk about two types of regression models. The first is principal component regression. The second is partial least squares. Both of these are what's known as biased regression techniques. Now, when we talk about this type of bias in regression, you may recall a regression is unbiased because the expected value of our parameter estimate is the population truth. So what I have on the left here is the mean of the distribution of all possible sample parameters that we expect to be the population truth. Now, in a biased regression, this is not true. And it's not true on purpose. Let me try to motivate why we might purposefully bias a regression. What we're encountering here for the first time is the bias-variance trade-off. Now, I'm not going to get too far into this because it's something we'll pick up again in data mining and machine learning. So for now, I just want you to kind of visualize this idea of throwing darts at a dartboard, trying to get to some target being the population truth. And every time I throw a dart, it's like taking a sample, creating a regression, getting a set of parameter estimates, and trying to get the population truth. So if I have a model that's unbiased, but not precise, meaning it has a lot of variability, it means that, most of the time I am off target. But on the average, if you were to average all of those parameter estimates, I would get to the bullseye. On the right here, I have a situation where my dart throws, my attempts here are biased because the average of those parameter estimates is not the population truth. But my variability has shrunk considerably. So I've traded the introduction of a little bit of bias for a big reduction in variance. And as such, I'm actually closer to the truth much more often than I was on the left. Now, what do you lose when you do this? Well, you lose all of that statistical testing of significance. Remember, the idea of hypothesis testing comes from a null distribution, and you need to be able to describe that null distribution. We'll no longer be able to do that in a bias technique. And what do you gain? Well, hopefully you'll gain some predictive accuracy on validation data. Biased regression is one way that we deal with multicollinearity in regression. If you'll remember, PCA gives us this new representation of our data in a new basis that's completely uncorrelated. Now, the trick here is that if you use all of the principal components, you don't actually solve the problem. You just hide it through rotation. The problem was, in another set of words, that you had a nearly zero eigenvalue. You haven't solved that problem by writing your data in a basis of principal components. Your eigenvalues have not changed. It's actually a theorem. Orthogonal rotation does not change your eigenvalues. So if you had one near zero, meaning you had a problem with multicollinearity, you still do now. So you have to drop some components to solve severe multicollinearity. When we set out to make a regression model, the goal is to model some target, y, as a function of your input, x variables. Of course, these x's are just the columns of your original spreadsheet. And so what we're going to do is instead use the principal components. And these would be the scores for each observation on each component as our new predictor variables. So up here, I was using the betas to represent the coefficients. Down here, I've changed that to represent the alphas. And I'm just putting my principal components into a regression model. Now, what's wrong with this expression compared to this expression? We lack interpretability. We used to be able to say for a 1 unit increase in XP, Y will change by beta P. Down here, we could still say for a 1 unit increase in prin K, but someone's natural question back will be, what's prin K? I gave you P variables, like X1 through XP. What is this? Well, there's an answer to that, and that answer will actually help us rewrite this equation back in terms of our original variables. Because each of those principal components can be written as a linear combination of the original X variables, where these V11, V21, these are entries in the eigenvectors. These are loadings, right? The loadings are what gives me the coefficients on the X variables. And so that will help us get back to our betas. It's like one big, massive substitution because I have one of these expressions for each principal component. So the next slide is going to show you that replacement math for correlation PCA. Here, keeping in mind that I have to standardize my target variable because in the background, this didn't have to be done by me, but it will be to rewrite it. In the background, all of my data was standardized. Okay, so I put those principal components into a regression model to predict the standardized Y. Keep in mind that they're linear combinations of standardized X's, and these are the betas that I'm trying to solve for here. So I wrote out that expression, and these two formulas at the bottom give you the expressions for each beta and the intercept. Now, I'm not going to hold you responsible for this math. I've done this for you as a favor because not all software packages have the ability to transform back for you. And even if they do, you can never guarantee they're doing it right. So there it is. When we come back, we'll talk about choosing the number of components for a principal components regression.